And like I described in the last lecture, bit banding is nothing but mapping of a complete word, okay, onto a single bit memory. Okay, so one single bit, okay, is mapped to a complete word. And now because the system is 32-bit system, so the word size is 32 bit. So one bit is mapped to 32 bit. We will see this in example also. So this is bit banding. This is one of the biggest findings, or what we can say advantage of uh, RISC architecture based on ARM devices. Okay, now, so in general, 1 MB of RAM is mapped to a 32 MB of IO port region. So in this way, you can see the RAM mapping of a memory from one region to another region. So 1 MB multiplied by 32 will give you 32 MB. So generally, if you see here, we have four regions: user program code, program data. Program data, when we say it is RAM, okay. Program data means RAM. Peripherals like your GPIO, ADC, DAC, timer, all those peripherals, and of course the interrupt and all. So these are the memory ranges which are mapped from one memory to another memory, and we have discussed it in the previous lecture also, that 1 MB of memory space is mapped to a 32-bit MB of space and all. Okay, so now the question is, how can we find out, what is the equation to find out that this memory region is mapped to an alternate memory region? Then what is the equation for that? So bit band alias region, alias means the second name, we can say. Like for example, your name is okay, your name is assume your name is Deepak, okay, but alias means you are also known as for example uh, Deepu, okay. So this kind of aliasing, so that means it is also known as, so it is mapped, okay, it is also known as. So bit band alias region is calculated by using this formula. First you have to know the bit band base address, okay, base address. Then after that you will have to find the byte offset. Then you will have to multiply it by 20 plus bit number multiplied by 4. This is the equation to find the bit band alias region. So each bit can be mapped to any other memory region. For example, so bit 7 of address 20002000. What does that mean? Okay, it means because this is an hexadecimal address. Okay, so address is 20002000. Okay, so this is our address, and we know that in this address we can store a data of 8 bits, right? 8 bits, 1 byte. So D7 6 5 4 3 2 1 0. So these are the specific bits of that particular address. This is the address. Okay, now bit 7 of this, so suppose you are trying to find out what is the bit banding address for this bit. This bit is mapped to which address? Because this is the 22 2000 if it is the address, and D7th bit where it is mapped. Okay, you have to find that, and provided you have the top equation with you. So base region is 2200.0000. This is the base address of 2000. So this base address plus offset, byte offset is 2000 multiplied by 20, hexadecimal 20. Okay, so you multiply it by 20 plus bit number. Bit number is 7th bit, bit 7. So 7 into 4. So when you calculate this particular number, you will find that it is mapped to 2204001C. So that means this bit is mapped to a memory which is 0x22040001C. So in this address, if you write 1 in this address, again remember this address also contains 8 bits, right? So if you write 1 in this particular address, that 1 will come here and it will be written like this. You can only write 0 or 1 in this particular register. You will not write any other number other than 0 or 1. So if you make it 0, all the bits will become 0. Then this bit will also become 0. Okay. If you make it 1, all the bits will become 1, or you can say FF, and this D7th bit in 2000 will become 1. Similarly, you can calculate any other region for bit banding. Okay, so first you must know the base address. Now these are the things to remember. Okay, I will when we will see the memory in total, then things will become much more clearer. Don't worry. So please keep note of this equation. Band base address, byte offset multiplied by 20 plus bit number, whichever bit you are actually trying to map, multiplied by 4 will tell you the bit band alias address. Okay. So what are the advantages of bit banding? This was one asked in the last class also. So remember, in ARM architecture, it follows this particular approach: read, modify, and write operations. So here there are 3 operations going to take place: read, then modify, then write. Right? So in between these 3 are going to take certain time to read something, then modify something, and then write that particular data. So to reduce this particular 3 operations, you can just, rather than going to read, then modify or write, you can go to one particular address, write it, and your job will be done. So it is fast, it is more faster. Okay. These 3 operations together are also known as atomic operation. What does that mean, atomic operation? These are technical terms which are find in embedded systems. So remember, these kind of questions are also raised. What is the atomic operation of any particular microcontroller? It is the smallest possible operation which the microcontroller can do. Okay, so an atomic, in case of ARM Cortex-M4, this is the atomic operation. That means read, modify, and write sequence. Okay, keeping in mind without any interference. What can be the interference between these 3? Anyone? Can anyone tell me, when the microprocessor is doing read, modify, write, what can be the interference in between that? Can there be any interference between these 3? Because I am saying this is the smallest job or the fastest job a microcontroller can do. So in that case, between these 3, who can interfere in between these 3?
Interrupts.
Right, interrupts. So now, because interrupts can come here in between because interrupts are asynchronous. You know this thing, this term, asynchronous. What does that mean, asynchronous? Synchronous and asynchronous. Anyone? You might have heard these terms many a times. Synchronous and asynchronous terms.
They do not depend on the clock.
Right. They do not depend on the clock. So synchronous events are those events which wait for the clock to complete. Asynchronous are those events which can come anytime. So even in between these 3 operations, suppose you press the switch and that switch is actually connected to an interrupt line. You can press the switch anytime. You cannot wait and see higher read operation is complete or not, modify operation is complete or not, write operation is complete or not. Okay, write is over. Now I have to interrupt here. You cannot wait like this, or you cannot give an interrupt like this. You can press the button anytime you like. So at that time also, even in between the atomic operation, Okay, interrupts or some other requests may arise. So therefore bit banding allows you to avoid that scenario also, because in one operation, in one go, you can change one particular bit. Otherwise, to change a single bit, you have to go through these three operations. Whereas because of bit banding, you can do faster execution of us, or changing a bit faster in than the atomic operation also. Remember SRAM, we will see this memory mapping. Okay, SRAM starts from 2000. Okay, so if this is the starting address of the SRAM, this nothing is, this is called base address. Okay, base address. Okay, in the previous equation we saw that base address. So, so 2000 is mapped to this particular address 2200. Okay, this is the mapping from here to here. Okay, so now, so 1 MB of RAM is mapped to a 32 MB of another memory address, or we can say bit band alias region. Okay, bit band alias region. Similarly, one more important region of bit banding is for the peripherals. Why peripherals? Like I said, GPIO is a peripheral. GPIO. When we say GPIO, A, B, C, D, E, these are all GPIOs. So A, port A contains 8 bits, right? And suppose, for example, D7, D6, and so on up to D0 of port A. Okay, if you want to just connect an LED here, and you want to just make this LED on, D6th LED on, and without disturbing any other bits of port A, in that case you can use bit banding's property, because you can directly go to an alias region, okay, and change the bit D6. That is your choice. So base address of peripheral starts from 4000. Okay, so 4000 is mapped from here to 4200. Okay, so these are the two important alias regions for the SRAM and peripheral address. Rest we don't have to worry about the part. Okay, so both 1 MB of region or 256 MB here is mapped to this particular memory. Okay, so this is all about bit banding. That means one bit is mapped to a 32-bit register or an address. Okay, so what are the specialities of this particular microcontroller? Because we were talking about Cortex-M4. So TM4C123GH6PM, it is designed by TI, Texas Instruments. So what are the features available in this particular IC? So this is the IC in the board which we are going to program. It has got 32 KB of SRAM. SRAM will store your variables and data. Okay, so that is there. 256 KB of flash memory. Flash memory means the memory in which you can keep your codes. So generally user code is kept in this particular flash memory. Apart from that, EEPROM is also available. 2 KB of EEPROM. These are dynamic variables which are going to change in between the program also. Okay, so dynamic variables, or dynamic, okay, variables, okay, which may change between the program also. So 2 KB of EEPROM. So basically we will focus mostly on this particular region, 256 KB of flash, where we will keep our program. So we cannot write a program bigger than this, otherwise we can use external memory also. And 32 KB of RAM. Okay, so we have very limited memory for writing our program. Apart from that, it has got internal ROM, that the ROM is loaded with this particular TIVA C trademarks of C series software, that is booting up and checking up the hardware and all. So this is the software which is pre-installed in the microcontroller, this microcontroller. Okay. Okay. So where we can download this TIVA TM peripheral driver, for that you can go to this particular memory address, the web page. So I recommend you to go to this particular, if you are going to use the board, okay, you can go to this particular address, ti.com/tools/sw minus sign TM4C. Okay. So please go to this memory address and you can download your software from here. Okay, this particular address. Okay, so it is not that you can directly go and download it. For that, here is the download option. From here you can download the software. When you click here, this is the link where you have to download. Okay, this is the latest version, full release. When you click this, it will ask for you to register in their website, because they want you to comply with the United Nations, USA's some rules and regulations. Okay, anyway, you can, it is, the registration is free, so you just register here and you can download the software. Okay, and install the software after you download it, because this will provide you the driver libraries for your hardware. Apart from that, you will need bootloader. Okay, bootloader, because sometimes what happens, by mistake, sometimes what we do, we write some of the registers which are not meant to be written. That means sometimes, for example, there are some registers which allow you to communicate with the serial port. So the microcontroller board, let me just show you what I mean by that. Okay, so we have the microcontroller board. Okay, microcontroller board, and we have our PC computer. Okay, so the computer and our microcontroller is communicating via a USB. Okay, so MUP board, MUC board, microcontroller board. Okay, even in this, for example, you are using TX and RX line. So TX and RX are actually controlled by some internal registers, which actually, when enabled, do the transmission part. When disabled or enabled the RX line, you will receive the signal. So suppose by mistake you programmed this particular lines also, suddenly the communication between the computer and the board will be broken. And now how can you, because this register is overwritten by you, so after that you cannot communicate with between the USB, using the USB line, you cannot communicate with the PC. So for that, in such scenarios, you have to use this particular LM flash programmer, which will help you to reboot the system using the basic booting software. Okay, so keep this, if in future if you have any few issues with uh, booting the system, or if you get errors like the board is not detected or something like that, then you can use this flash programmer. Again, for downloading, you need to register in their website and download it for free. Okay, it is not they are not going to charge you, just you need to provide the details. Let me show you what kind of details they need. Let me check. Okay, good. I don't have the login. Okay, let me check. No, wrong. Sorry. Okay, got it. So here you will just have to click on civil, and you will say that yes, about true. So you are not going to break these rules. Please read them before submitting, and then after submission you can download the software. Okay. Okay, done. So this is all about the softwares that you have to download for this particular board. Apart from that, this board also provides you advanced encryption standard cryptography table. Okay, so this is also available apart from the vector or NVIC data. It also provides you AES. Have you heard of AES encryption? This is also available in your Wi-Fi dongle or most of the time routers also. So there are some encryption techniques which are pre-installed in this board. So this board is going to provide you that AES cryptography table. If you need to do some encryption, decryption kind of programming or cryptography related programming, you can use this particular pre-installed cryptography table. This board also provides you CRC, that is cyclic redundancy check error detection functionality. This is one of the techniques which is used to check the error when you are going to use communication between two or more devices. Okay, so there are many other error correction. Have you heard of error detection and correction codes? Have you heard about this particular term in any of the subjects?
So you mean the convolution code, linear block codes and all?
Convolution codes are not error detection correction. I don't know. I'm not sure about that. But error correction detection,
We read these in digital communication.
yeah, in digital communication, you have this kind of error
Yes, the
correction and detection
cyclic
codes.
codes and all. Yes.
Yeah, yeah. So CRC is used for detecting error and correcting them. Let me check what are the other codes. Hamming code and all are there.
Yes, sir. Hamming code.
Error detection and correction codes. So there are many different techniques to correct, to find the errors and then correct them also. Okay, some are only the error detection codes. There are some codes which are only error correction codes. Some are both. Okay, so you can go through this kind of convolutional codes. Okay, there are two main categories: ECC codes or block codes and convolution codes. Okay, please go through this, so it will help you to Hamming codes and all. Okay, so these are the different techniques which are used to find if there is any error in the bit sequence that has been transmitted or received. Okay, so this board is going to provide you CRC based error detection functionality. Okay, now coming to the memory map. Now let us see the memory which are available in this particular microcontroller. Okay, TM4C123GH. So like I said before, it is a 32-bit system. So you have total 4 gigabyte of address. Okay, and this 4 gigabyte of address can range from 00000000 to FFFF. Okay, so within this region itself, you have all the addresses, be it for the RAM, be it for the peripherals or any other vendor dependent registers. So every particular type of register is within this particular range of address. So this is following memory mapped. Have you gone through memory mapped IO? Can you recall this particular term, memory mapped IO?
Yes, sir.
What happens in this technique? Everything everything is considered as a memory, right? So whether you are going to handle an IO device or you are going to handle a memory, the CPU do not understand the difference between that two. Here everything is memory mapped. Okay, if in 8085 there were two separate memories that you can mapping techniques were there. One is IO mapped IO, where the address was 7-bit, where you had 8-bit addresses, and the other was 16-bit addressing. 16-bit addressing was for the memory mapped, 8-bit addressing was for the IO mapped IO. So but here you don't have to worry about that part. This system or microcontroller that we are going to use, or ARM Cortex-M4, follows memory mapped IO. So even if you are going to make an LED on or off, you are going to use memory mapped IO technique. So you will be writing in a memory. That memory will be representing even an LED also. All the GPIOs, timers, ADC, DAC, all the IO devices have an address which is actually mapped in the memory mapped IO. So all the addresses are 32-bit addresses for the IOs also. Okay. Now on chip flash, like I said, the user program will reside here. User program will reside in the flash. Range from 00000000 to 003 FFFF, that is 256 kilobyte of memory. This is the size for the user program. SRAM, the RAM ranges from 2000 say 10 is missing here, sorry. Okay, 00000000 to 2007 FFF, that is 32 KB of RAM. Okay, and peripherals address start from 4000. Peripherals address. Okay, when I'm saying peripheral, it includes GPIO, timer. We will see that. Okay, timer and ADC, DAC, you name it. All the peripherals which are available in this system, they will start from 4000 and they will end at this particular address DFFF FFFF. Okay, so let us see the mapping. Okay, so first of all, 256 KB of RAM. So the, if you can remember from the 8085 also, the initial addresses are kept for which particular task. If you can remember, in
Interrupt.
8085, the interrupts, the first few addresses are always reserved for the interrupts. So you see here 00000000 to 00000008. This is all reserved for exceptions and interrupts. Both are kind of interrupts also. Okay, you can say, but exceptions are more hardware oriented tasks, and we will see this vector table also. So this is all about the interrupt vector tables. Then after that, you have system control registers, which are ranging from B0 to 268. Then of course, you have the 256 KB of user flash RAM, or you can say flash memory, starting from 0002 to 3FFFF. Okay, this is our 256 KB of memory. Now coming to the second part, 16 MB of internal ROM. This is kept apart for the TIVA, that is the vendor specific driver libraries, bootloader, AES, like I said, the encryption part, and error correction and detection related codes. So this is all covered by the TI. So TI will be taking care of all this memory. So they have kept their particular softwares, drivers, encryption tables, and everything in this particular memory. 16 MB of memory they have kept for themselves. Okay. Now, apart from that, you have 32 KB of SRAM, which is for the user data or for the RAM purpose. So this RAM is the user memory, okay, for the user data, but this particular RAM is also mapped to the bit band aliased region. Okay, so bit band alias to 2002 map to 2200 and similarly onwards. Okay, so done. Now coming to the next memories that we can check here. So for that, I gave you some documents in the classroom. I'm going to show you the memory map from the data sheet. Please open this data sheet, and if you check here, coming down, you can see here, this is the memory map provided by the company itself. So see here 0x, this is hexadecimal representation. So 00000000 to 3FFFF, it is on chip flash. If you want to further read about this particular memory address, you can go to page number 540. And similarly, so bit band SRAM starting from 2000 to 2007 FFFF. It is mapped from that memory address to this. So if you want to just change one bit, then you can come to this address 2200 to 220F FFFF, and you can write something, and that will be reflected in this particular bit band SRAM region. Okay. Similarly, you come down, like I said, peripherals have their own addresses. So if someone asks you what is the starting address of watchdog timer 0, it is 4000. So this is the first address, and this is the watchdog timer's address, starting address, and the range of address provided to this particular is 4000 FFF. So just see here how much memory is watchdog timer taking. If suppose someone asks you how many registers are dedicated for watchdog timer, what is the answer? Hello? How much memory is reserved for watchdog timer? Can you see the screen?
Yes, sir.
What is the range of memory? I told you in the last class also, please keep this kind of calculator always with you. FFF.
4
How
KB.
much? 4 KB. Can you tell me why one particular watchdog timer is taking 4 KB? Okay, leave that part. Maybe watchdog timer, you don't know about that. You see here, GPIO A, that is port A. Port A is also taking 4 KB of memory. So what is the starting address? 4000, 4000, and the ending address is 4004 FFF. So it is also taking 4 KB of memory. Why we need 4 KB memory for 8-bit port A? Are you getting this question or not? Anyone? We have an 8-bit port. Port A is 8-bit. But it is taking 4 KB of memory address, or 4 KB registers are allotted for only port A. Right? So this mystery has to be solved. Why 4 KB of memory is provided to each peripheral? 4 KB for port A. If you come down port B, you can see here again this one. Anyway, so some few things which are very important when you are going to write a program. First of all, you must know what is the base address. Understood? What does that mean? Base address. If suppose someone asks you what is the base address for GPIO port B, base address. Base address is this one. Okay, this one, and offset is 5000. So base address plus offset will take you to this particular address. Okay, so please we will go through this, but anyhow, please open your data sheet also and keep an eye on these things. So here, if you see here, GPIO port A address is 4000 to 4004 FFF. But there is one more surprising thing. If you come down, and you might see here again we have port A, which is starting from 4005 8000 to 4005 8FFF. Again 4 KB of memory, again for port A. Understood what I'm saying here? Hello?
Yes, sir.
So there is one port A, but there are two addresses for that. So if you read here, one address is 4000 starting address. Another address is starting address is 4005 8000. So this is second question now. So first question is why we need 4 KB of memory for an 8-bit port. Okay, these are the questions to be asked now. That is, first question is why we need 4096 registers, right? Registers for an 8-bit port, right? Second question, why there are two different addresses for port A and so on up to port F or whatever, port E or so. Okay. So these are the two questions to be answered. Okay. So we will be investigating these parts. Keep this in mind. Okay. So this is what we are doing from the data sheet. So when we opened the data sheet, we found in page number 92 that the memory map talks about the memory, different sections of memory in the microcontroller. And you noticed that port A is starting at 4000 and it is ending at 4004 FFF. That means it is taking approximately 4 KB of memory for an 8-bit port. So, but the second observation was port A is also available in another address, which is 4005 8000 and 4005 FFFF. So these two questions are to be answered or to be investigated. Keep this in mind, okay? Because let the surprise be there
Yes,
and we
sir.
can. Boliye.
So is it something related to buffer?
No, we will come to that. Keep this in mind, okay? Keep this in mind and we will come to that answer later, okay? So this is the mapping here. This you can also see from the data sheet. I showed you the data sheet, okay? So I'm not going to talk about them again. So these are all the peripherals and their starting and ending address: ADC0, ADC1, analog comparator, CAN, USB. So if you are interested to change anything related to USB port or to use the USB port, you will have to program these registers. We will explore these registers also, okay, so that you can program them. And by programming it, you can start using the USB port with the microcontroller, or even you can connect your own devices at the USB. Okay, so this is how the register mapping is taking place. So, starting address, ending address, and the name of the peripheral. Okay, so please, when writing any driver software or writing a program for these addresses, you will need to know the these basic informations, then only you can program them. Okay, now coming down. So this memory map I show you. Okay, I showed you. So table number 2.4. Please download the data sheet and cross check these memory addresses. So whether you take it from TI or whether you take it from any other microcontroller board, first thing that you should know is the memory mapping, the addresses of each peripheral or the list of peripheral and their respective addresses, starting and ending addresses, and then further we can explore. Okay, we will come to that. This I have showed. Anyone having any doubt or difficulty in this part? Anyone having any difficulty to understand what is this particular table showing? Hello.
Excuse me, sir.
बोलिए.
So you said like the it's taking 4 KB. So you said it's taking 4,000 registered. How did you
Four
say that?
4096 na.
Yeah, how actually I'm confused. How
1
did you?
KB 1 KB is 1024.
Then but the register is of 32-bit size.
No, 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 no. 7FFF. Wait. So okay, wait a second. Let me show you here. Starting address is 2000, right?
Yes, sir.
Ending address is 2007FFFF, right?
Yes, sir.
Right. So let us go to the calculator and check. CE 7FFF. This is the range, right? 7FFF.
Yes, sir.
So 0 to 6, so yeah, 32 KB. Sorry, I'm my mistake. 32 KB. Okay, 32 KB of memory is taken. Correct. No issues. Okay, clear.
Okay.
See here, you have the calculator, na?
Yes,
In the
sir.
calculator, go to the programmer calculator. type in the hex, you will type the hex and you will get the range in decimal. Okay, yeah, 7FFF. My mistake, I was doing FFF. Okay,
No, sir, but you were doing it for GPIO
port,
port.
port also, see, fourth, yeah, so, sorry. This is the address for bit banded region, 32 KB, my mistake again. So port A, if you see here, starting address is 4000,
Yes, sir.
ending address is 4004FFF. So if you minus them, you will get
FFF.
FFF. So it is taking 4096, okay, including 0. 4096 memory addresses.
Yes, sir.
That is 4 KB memory addresses.
Hmm.
So 4 KB means 4000 registers are being used. 4000 registers are being used only for port A. I will show you that also. Okay, each register again of 8 bit. Okay, the address of those address are 32 KB. You see here the address is 32 KB.
Yes, sir.
4000 4000. This is address. The address is 32 KB. Sorry, 32 bit. 32 bit address. But in that address, the data is of
8-bit.
8 bit. Okay, so we
Oh,
will go through that. And but in these addresses, when we go to these addresses, because like I said, each register in the ARM Cortex, okay, is of 32 bit. When we will explore these registers, we will see 32-bit registers only, okay, in these regions, and then we will come to that. When we will dealing with the data, 8-bit data, but registers are 32-bit registers. So I will show you that. Don't worry. Okay, when we will go to this address has got a 32-bit register. How many registers are allotted to port A? If suppose someone asks you how many registers are allotted, 4095. It is 4 KB. 4 KB registers are allowed, or you can say 4096 registers are allotted to port A. How many bits are there in port A? Usable bits, 8 bits. You can connect 8 LEDs to port A or 8 switches to port A. But how many registers are there to program port A? 4096. So now the question is, what are these 4096 registers going to help you? And why we need so many registers? Because you needed only 8 bits, right? Instead of 8 bit, why we are using 4096 registers? So we will explore this part also, because for that you have to go to page number 658. Understood? So just imagine 658, page number 658 will give you all the details about these particular registers and all. We will explore that part. Okay. Let me briefly remind what to say, talk about this again, clear this thing. Starting address is this address for port A, right? This is the address, and it is 32 bit address. Clear? This is 32 bit address. In this 32 bit address, there is a register. You have a register. This register is also 32 bit register. And what is the ending address? So this is the starting address. Ending address is 4000.4FFF. So this is your ending address. Again, all these addresses are 32-bit registers. So what is the range in total? If suppose someone asks you, is FFF. That is the number of registers allotted to port A. How many registers are there? 4095 or 024096. In that terms, we can say 4K registers are allotted. Okay, because 1K is 1024. Okay, so therefore we are calling it 4K memory addresses or registers. And how many bits are there which can be accessed by any user? Port A has got D7, D6, similarly up to D0. So that means in total 8 bits are there, and these 8 bits can be used to connect LEDs or to use to control your switches and all motors or whatever peripherals, external peripherals you want to connect to these ports. So in total 8 bits are there which are you are going to control these 8 bits using so many different registers, or in total 4095 registers. So we have to explore what are these registers, what are their internal bits, and by changing the bits of these registers, what we can change here in this particular port as well as the bits of the ports. Okay, clear?
So total registers would be 4K into 32.
Bits na, no 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 no, registers are this much na,
Sir,
FFFF.
that's what I'm confused actually. How can you say if there are 4K bits, it becomes 4K register?
I'm
That
not saying 4K bit 40. Okay, I will disconnect the, okay, make it like this. 4095 registers, is it okay now?
so how
See here, the starting address is 0000, ending is here. So how many numbers are there between these two?
FF? Yes, sir. Okay, yeah, 4093. Yes, sir.
4095 numbers. What are these? 4095,
The
4095
register.
different addresses.
Yes, sir. Register एक ही address होगा.
Different addresses. And 4095 different addresses means each address has got 32-bit register.
Yes,
Understood?
yes, yes, sir.
So we will explore that, don't worry. This confusion comes when now definitely this should come to your mind, that again the biggest confusion comes to a mind is how come only to control 8 bits you need these many registers, and that too each register has got 32 bits. 32 bits are there in each individual register. So why I need 4095 into 32, that many combinations just to control 8 bits of a port A? Why we are wasting so many registers, or are we really wasting or utilizing some other features? We will come to this, because this is what the essence of programming is, okay, all about. So that will be explored from the data sheet. For that we have to check the data sheet, why these all confusions are coming. Okay, so we have the memory map done. So please keep this memory map in your mind, and then we will go forward. Okay, so first of all, we discussed about the stack in many occasions. One more time I am going to repeat this. So stack memory is used to store some temporary data which is related to branching instructions and all. So first of all, stack follows first in last out, or we can call it philo. First in last out, okay, philo system. Okay, whenever we pass a command push means data from the microcontroller will go to memory. Okay, push means is almost like store. Okay, so data from MCU will go to memory. Okay, memory. And pop means data coming towards MCU, okay, from the memory. Sorry, MEM, memory. So push and pop instructions are used to write or read something. Push, PUSH. Okay, let us see in more detail. So whenever we pass a push command, we know that each register can store only 8 bits. So 4 bytes, 8 bit means 1 byte. So 4 bytes of data should go to the memory. So we can break it down like MSB, MS, LS, and LSB. What are these? It means, I will show you this also. What MSB means. So most significant bit and least significant bit. Then most significant, least significant, not the byte. Okay. We will see what this 4 chunks means. So in total 4 byte of memory will be moved, because every time we move a data, it will be always 32-bit data. Okay, 32-bit data. So 32-bit data means if you break down into 4, that means 4 8-bit data. Okay, so 4, that's why 4 bytes are moved. I can say 1 byte, 1 byte, 4 into 1 byte. Okay, so whenever pop is generated, stack is initialized to the top of the stack, and then the data is moved or fetched towards the MCU. Okay, let us see the operation. It will be more clearer than the statements. So for example, you have a data in a 32-bit register, any register, wherever the data is there in any register. We can break it down like this: bit number 31 to bit number 24, we can call it MSB byte, and then 23 to 16 MS byte, 15 to 8 LS byte, and 7 bit number 7 to 0 LS byte. Okay, so how this particular data is moved when we pass a push command, okay, and how the stack is actually arranged. So here, this is how the data is moved. First the MS byte will move, then the MSB byte first, then MS byte, then LS byte, and then LS byte. So then this sequence is taking place. So the data first entered is the MS byte. Above that will go the next byte, then the next byte, then the next byte. Okay, if you see here, the starting address is 2000 5000. Suppose here was the pointer, stack pointer pointing at before push operation. After push operation, it will go upward. We know that. Okay, data goes upward. So it will be decrementing. So 2000, 4FFF, then 4FE, then 4FD, and then 4FC. So after one push operation, you see here 4 registers are occupied by the data which you have pushed into the memory. And this will be the new stack pointer's address. Okay, this we know. Okay, so remember, the stack always grows towards lower memory address. So stack grows towards lower address. This is what we followed in the 8085 also. Now this is the push operation. So remember, MSB byte goes to the lowest address. Now this data has been stored in the register or stored in the memory registers. What happens when we pass pop command in the of the embedded system or a 32-bit embedded system? Again, we can divide the 32-bit register into 4 different bytes. Naming start from 31th bit to 7th bit. So MSB byte, MS byte, LS byte, LSB byte. Now how the pop instruction actually works. So to fill the register, remember, it follows just opposite to that of push operation. So the pointer was here. Okay, the stack pointer was here, current stack pointer was here. So first data goes to the LSB byte, then LS byte, then MS byte, and then lastly MSB byte. And after pop instruction is over, the stack pointer comes back to its original position, that is suppose 2000 5004. So stack is growing downward when you use pop instruction. Okay, so push instruction, whenever you pass push instruction, the stack grows upward. Whenever you do pop instruction, the stack goes downward. Okay, any doubt in this part, push and pop? Because this we covered in 8085 also, so I don't think there will be a big doubt in this part. Anyone having still any doubt in this part? Push and pop, how the data is moving from memory to the register, or temporary register, or temporary register to memory? Anyone? If not, okay. Then let us go to the next part, that is interrupts and exceptions in Cortex M4. How? Because whenever we talk about stack, it is mostly related to branching instructions, and whenever we talk about branching instructions, one of the common branching instructions are related to interrupts. Okay, first of all, we must know the exception and interrupt table. What is the range of exception and interrupt table? Let us go and check what are the exception and interrupt tables available in ARM Cortex M4 microcontroller. For that, I am going to the data sheet. Okay, so here you can see the exception types. Okay, now, okay, first of all, I will show you the interrupts. You see here interrupts 0 to 15. First 15, or you can say 0 to 15 means 16. Okay, so anyway, so 15 interrupt levels are called these exceptions. First 15 are exceptions. Let me just comment. Okay, no, there is the comment. Oh, drawing. Okay, so here this is the boundary region. So 0 to 15 are for exceptions. So remember, exceptions have higher priority than the interrupts also. This thing you have to keep in mind. The exceptions have higher priority than interrupts also. So processor exceptions, I will show you what these exceptions actually means and why they have higher priority than the normal interrupts also. Okay, then after that we start the interrupt number. That is, if you talk about the vector tables address 0 to 15 for exceptions, vector address 16 is allocated for, sorry, is allocated for the 0th interrupt, and 0th interrupt is for the port A. Then it goes onward 0, 1, 2, 3, 4 and so on. So 0 to 15 exceptions, and then 16 onwards are your interrupts, or you can call interrupt number 0, interrupt number 1, 2, 3, so on. But actually vector address is 16, 17, 18. Anyone having any doubt in this part? Two things you have to remember. Okay, first is exceptions have higher priority than the interrupts. Okay, second thing that we have to remember is after 15th interrupt, the first interrupt we can call it as a 0th interrupt, or if you are referring to the vector address, it will be 16th. Okay, that's the only thing that you have to remember. First two things that you have to remember: exceptions are having higher priority than interrupts, and then only after that interrupt starts. So how many interrupts are also there in total? How many interrupts this particular microcontroller supports? If you go down, you can see here it supports almost 138 interrupts, 138 different interrupts. If you ask the vector range, so vector address starting from 16 to 154. In between that, there are many locations which are reserved, which are not used. Okay, for example, 107 to 133, they are not used, they are reserved. Okay, similarly, you can come here and you can see 72 to 91 reserved, not used. Similarly, 64 to 67 not used. So you have to keep an eye on these vector table whenever you are going to write ISR, interrupt service routines. Okay, you must know few things like the interrupt number, the address of that interrupt, and if you want to know the vector number, then the vector number also. But mostly we will be dealing with these two numbers. Okay, the interrupt number and the address. These two, at least we should know these two things: the interrupt number and the vector address of that interrupt. We will go through this in more depth in the coming lectures, but these are all the memory mapping I'm showing you. Okay, so 0000, if you see here, starting address is allotted to exceptions, and all the starting addresses, you see, the if suppose someone asks you what is the page number for vectors, page number, can anyone tell me the page number? In which page are these interrupts located? Page of the memory. Anyone? What do you mean by page?
So from 000 to 000FFF is a
No, no.
page.
Page means the main address. For example, 0th page. You see here, all these addresses are starting at 0000. This is our page. In the page, you can see the line number, right? This is how we differentiate these things. Okay, so page number, and then we can go to the line number or so on. But anyway, even if you don't remember these things, just remember the vector address, and that too you don't have to remember it. You can refer to the data sheet. So whenever you have to check, suppose someone asks you what is the interrupt address for ADC1 here, so you can just directly go and see here this particular address. Then we will write program to change this particular register. Okay, we will see how to do that, but at least you should know the address and the vector number. Okay, then we will be writing C program to manipulate these contents of these registers and all. And what are the programs, how we do that, that we will see when we will be going through the C programming. Okay, but first of all, we are going through the architectural details. Okay, then anyone having any doubt in this part? What are interrupts, how we check that their vector addresses, and how we check their offset addresses or the ranges, what are exceptions and what are interrupts, which is having higher priority. Otherwise, for example, if suppose someone asks you what is the interrupt number for exceptions, can anyone tell me? If suppose the first interrupt starts at 0, which is for port A, can you tell me what is the interrupt number for exceptions? Interrupt numbers for exception. Otherwise, how can you translate this thing, interrupt number? If suppose you don't, if you are not asked vector number, interrupt number of exceptions, here this particular interrupt number, how can you bring to that number? Anyone? Interrupt number of exceptions. Is it that difficult? Please put your common sense and tell me that. No, it is not that difficult here.
Vector number -16.
Minus. So -1, -2, -3, -4, because interrupt number 0 is for port A. So interrupt number -1, -2, -3 will be going for the exceptions up to 15. Go upward up to 16, right? This is how we check that. Okay. So sometimes in many so-called data sheets, if you might be possible, you are going to study about STM32 or some other microcontrollers. In that, they may say that this interrupt is negative interrupt, and then you will think what happened, why we are having negative interrupts. Those are not negative interrupts, rather those are exceptions, but the data sheet of that company preferred to write it -1, -2, -3, and so onward. Okay, please try to understand these things also. Okay, so processors are up, or we can say exceptions are negative interrupts also. They have much more higher priority than normal interrupts. Clear? Or do I need to explain it more? Okay, so there are two things in any microcontroller. One is exception and the second one is your interrupt. So both are actually used to handle the fault. Yeah, interrupts are also used to check some important thing, mostly faults or something like that. So these both exceptions and interrupts are generally used to handle faults or some important functionalities. Okay. NVIC, nested vector interrupt controller, is one section in the ARM Cortex microcontroller, and it can control up to 240 interrupts and exceptions in total. Maximum, okay, can handle up to 240 interrupts and exceptions. Okay, so there are 15 exception types of exception, 15, ranging from 1 to 15. Okay, this I talked to you also. Exceptions with greater number than 15 and above until up to 250 are considered interrupts. So 15 onwards, that means 16, 17, 18, 19, 20, up to 240 are interrupts. So you can call from 0 to 240 interrupts. Okay, interrupts, and minus 15 to minus 1. Okay, minus 15 to minus 1 are exceptions. Okay. Exceptions. We can read it in different ways. Okay, remember, the smaller the number, the higher the level of interrupt or exception. So if suppose you have two interrupts arriving at your microcontroller board, one interrupt is coming from suppose 25th address, and the second one is coming from 02, two interrupts are coming. Okay, then in that case, higher priority is always for the lower address. So lower priority. This is all the same with the 8085 also. So if we know those basics, it won't be that difficult. So which one is having higher priority? The smaller the number, the higher the priority. Okay. So what are the different types of interrupts or exceptions? There are two types. One is software related exceptions or interrupts, or hardware related exceptions or interrupts. For example, if suppose someone asks you what is software based interrupt or exception, it can be divided by 0. Any number divided by 0, suddenly you cannot do that mathematics. So what will happen? It can generate an interrupt or an exception by the microcontroller itself. Might be possible you have not written a separate interrupt service routine, but because this type of conditions has to be handled, for that might be possible exceptions are defined in the microcontroller. Similarly, some errors related to watchdog timer or ADC or something related to some hardware, that can also be an exception. I will show you that part also. So there are so many things to cover. Okay, when I'm saying I will show you, please make note of those things, because in future you have to check that part also. So let us see the types of exceptions which are available. Okay, so we talked about the interrupts. Let us see the exceptions. What are the exceptions? Inactive exceptions. Okay, states, exception types. Okay, reset, right? It is an exception. Whenever you press the button or the power button or you reset the system, it is an exception. Suddenly the microcontroller has to stop everything, restart the whole system with 0. The memory 0, the RAM 0, the program starting address 0. So it is an exception. NMI, non-maskable interrupts. Those kind of exceptions are also there. Hard fault. Hard fault means, that means those fault which cannot be handled by the software part. Okay. So those kind of exceptions are there. Memory management fault. What does that mean? Can anyone tell me what is memory management fault in general? What can be the memory management fault? Okay, I discussed about these parts, the memory architecture for the ARM, and I told you these are, for example, these are different memory regions, right? There is a region for flash, there is a region for ROM, there is a region for SRAM. Suppose you are writing a program which is storing some variable in the SRAM region, in this region. Assume you are storing something in this region, but while storing, maybe you are storing it deliberately, or maybe you unknowingly storing it. For example, stack or something else is storing some data. Suddenly this region, assume, okay, the data from this region goes into this region, stack. Yeah, you see here 2000. You started storing the data from stack and it grows upward, stack grows upward. So you will, might be possible you may reach up to this region also, or you might possible you may enter into this region. So what happened? What you will call this particular error?
Memory exception.
Yeah, memory exception, because you are not allowed to keep your data in this region. It is not allowed. Similarly, it is not allowed to keep user data in this region. So you are doing memory error, which is not allotted to you. You are trying to access those memories, or those kind of data are trying to access those memories. So that is called memory exceptions. Okay. So those kind of errors are also possible. Now coming to another bus fault error. I will show you this bus fault error. Uh, what does that mean? Buses means the lines which take data from one device to another device. So there are specific buses allotted to different memory regions or peripheral regions. Suddenly, if you change those buses and ask them to do something other than that, they will throw you an error which is called bus fault. Okay, bus fault we will see when we will see the internal bus architecture of the microcontroller. Similarly, usage fault, undefined instruction. If you try to do some undefined instruction, illegal unaligned accessing, invalid state or instruction, so those kind of exceptions are called usage fault. So these are all exceptions, important parameters. Okay, so system timer related instructions, interrupt related. So these are the, here you can see the table 2.8 exception types. So the first exception is stack top is loaded here. Then you have reset, non-maskable interrupt, hard fault, memory management related issues, bus fault related issues, usage fault, reserved, then SV call, debug monitor. So these are the interrupts here. Okay, so please go through the data sheet to check where are the exceptions. Table 2.8. So these are related to exceptions. Again, like I said, they have higher priority than the interrupts. So they handle more serious issues or serious faults in the microcontroller or even in the programs. Right. Now let us move ahead. Nested vector interrupt control. Like I said, there is a separate unit which is totally dedicated to handle interrupts in the ARM Cortex-M4, and we call it nested vectored interrupt controller. Nested vectored because interrupts can come within the interrupts also, and those kind of interrupts are called nested interrupts. Okay, and vectored because each and every interrupt will have its own address. Okay, not going to the into this. Okay, how the interrupts are handled by the, or how the NVIC handles the interrupt. First of all, any interrupt will request or generate a request, okay, ISR, interrupt service request, from external source, okay, which is actually received by the MPU. So first of all, any interrupt which is generated by the external source will come to the MPU. Depending on that, might be possible, just like the 8085, might be possible that CPU is doing some other jobs. So CPU responds to the interrupt based on their masking registers or the priority levels. So these two things it will check whether the interrupt is masked or not. Masked means it is not allowed to come or not. If it is allowed, then what is the priority of that interrupt? Right? First the interrupt comes, then the CPU checks whether this interrupt is allowed or not, first thing. Second, if it is allowed, what is its priority? These two things the CPU will check. Then after that, if the interrupt is allowed and then it has to be addressed, then in that case, ISR is accepted and related ISR will be addressed. The address of or the vector address of the interrupt will be reached. Third step. Okay, this is just like 8085. So now the question is, before going to the ISR or before executing this program, the microcontroller should store some important data which are more relevant to the current instruction which he was doing, because the microcontroller has to jump from one memory location to another memory location. So what is his current job? He has to store all the current jobs related data in some memory. Okay, so that is pushed. All the data related to the current instruction is pushed into the stack. Okay, and for that, here in case of ARM Cortex-M4, it uses R0 to R3, R12, link register, PSR, and program counter data to the stack. So it is quite a big data. Okay, it will store that into the stack memory and then only it will go to the interrupt service routine. Okay, and while serving an interrupt, if he is serving this ISR, then he will disable the rest of the interrupts which are of lower priority, and he will receive or address only those interrupts which will have higher priority than the current interrupt. Otherwise, he will not listen to the lower interrupts also. So he will mask and unmask or enable or disable higher or lower level priority interrupts depending on the priority of the current interrupt. Okay, then the ISR is executed, and then after the when the ISR is complete, of course he will have to go collect all this data from the stack and come to the original program or the main program. So all the exceptions which were disabled will be unmasked. All the data which were stored in the stack will be popped or will be read back, and the program will come back to the main program and continue the normal application. So it is quite a lengthy process. It is just like 8085. Only thing is here you have more number of data which are stored in the stack, right? Of course, any interrupt comes to the microcontroller does not mean it will have to be served. For that, first you have to check whether the interrupt is masked or unmasked. If it is unmasked, then you will have to check what is the interrupt priority. Okay, if it is having higher priority, okay, I will serve that interrupt. But before that, I have to store the current instructions detail in the stack. For that, it is going to store some data in the stack, and then he will disallow all the lower interrupts and only allow the higher interrupts if they come in future. He will execute the ISR, and after completing the ISR, he will again allow all the lower exceptions or interrupts. Apart from that, he will read all the data which were stored in the stack and then come back to the main program. Okay, so if you see here in the graphical manner, this is the way it is done. So suppose the microcontroller is doing task 1, and suddenly after completing the task 1, he has to go for the interrupt. An interrupt is generated or exception is generated. So it will take some time. The microcontroller will take some time to store the data, current data. Okay, the program is here. So all the relevant data related to the current program has to be stored in the stack. So assume the stack pointer is pointing here in this address. Okay, it will go and it will take small time for the CPU to store the data in the temporary registers. So all the temporary registers, like I said, 8 registers are there. Their data will be stored in the stack, and this is the sequence in which the stack is filled: PSR, return address, the link register, and R12, R02, R3. So these registers are stored in the stack, and the stack pointer now points to this particular address. Then he will go to the ISR, interrupt service routine, execute that, and then remember, this was thread mode, normal mode. It entered into handler mode to handle the exceptions. Then after completing the exception, it will take small time to pop all the data which were stored in the stack. These are stored in the stack. Okay, so it will take small time to retrieve all the data which were stored in the stack. Okay, and then it will come back to the original program, and the stack pointer goes back to the original position. Is it clear? Or do anyone having any other doubt? Anyone having any doubt in this part? I'm going to end the lecture here. In the next lecture onwards, we will be talking about the instruction set, and we will be jumping into the C programming part. Okay.